From the last video, we talked about capacitors, and we talked about a parallel plate capacitor, and we had a charge source that was connected to two plates that are separated by some value D and have some surface area A. So A is the surface area of one plate. Now measurements can be made, and we can find a relationship between the amount of charge and the potential, which is this charge source is going to have a potential V, and it's a linear relationship. It's Q charge is equal to C the capacitance times V the potential. So let's look at how we can calculate the capacitance of two parallel plates. From chapter 22, the electric field for a conducting surface is E equals capital Q. Let me write that where I have a little more space here. E equals Q over epsilon naught times A. And now let's look at what is the potential across the plates. Well, if I have a plate or a point B on this side and a point A on the other side, then the integral, I got my letters backwards here. Sorry about that. It should be on this side and A on the other side. I'm going to have positive charges on the right and negative charges on the left. So I'm going to be integrating backwards along the electric field. So that's going to be VB minus VA is equal to the negative of the integral from A to B of the electric field times the differential length, and that's a dot product, times, that would be the cosine, but the cosine here is going to be 180 degrees. So this is the definition of a dot product. And I'm integrating in the opposite direction, so I have a cosine of 180 degrees. And now I can put in for my electric field. Take the cosine of 180 degrees, that's going to be a minus 1, so it takes out the negative. And I get the integral from A to B Q over epsilon naught A times dl, and this electric field part, Q divided by epsilon naught A, is just our constants, and the integral is just the distance between the two plates. Here's the electric field. So it's just the distance that the electric field is. So we have that the potential is equal to Q over epsilon naught A times D. Now let's solve our relationship for capacitance. So capacitance is equal to Q divided by the potential, and I can substitute. I know my potential here, and simplify, and I get epsilon naught A divided by D. So what does this tell us? Well, as A increases, our capacitance increases, and as D increases, our capacitance decreases. So this is the value of the capacitance for a parallel plate. Now, the next videos we'll look at some other configurations and find the capacitance for them.